Hello friends, this video on Semiconductors part 26 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 25 before going ahead with part 26. So now let us look at some of the applications of a transistor. As I mentioned you before also, the transistor was a very important invent of the semiconductor electronics. So, what are the purposes where transistor is used for? So here in this lesson, we will talk about two applications of transistor. That is transistor acting as a switch and transistor acting as an amplifier. This is a very important topic because this is one of the most important purpose of transistor, that it acts as an amplifier. It helps to amplify the input signals. So let us first talk about how transistor acts as a switch. So far what did we discuss? We discussed what is a transistor, what it consists of. It consists of emitter, base, collector. How are each of these regions doped? What are their sizes? What is biasing of a transistor? How does the current flow takes place inside a transistor? Right? And what are the characteristics of a transistor? That means how does the voltage and current vary inside a transistor? And what did we conclude from the transistor characteristics? That the output current or the collector current is driven by the input current, that is the base current. And there is a good relation between the input circuit and the output circuit of the transistor. Right? So now let us look at the transistor as a switch. How does a transistor act as a switch? So if you look at the circuit which is drawn here, it is a common emitter configuration. The transistor is in common emitter configuration because you can see that the emitter is grounded and it is common to both the other terminals. It is common with base as well as it is common with the collector. So how does transistor act as a switch? Now let us look at this circuit and see what happens as the input voltage is applied to the circuit and the input voltage is gradually increased. Now forget about the switch as of now. This is just a transistor which is in common emitter configuration and such that the biasing which is provided here, that is VBB and VCC, they are all variable voltages. You can change them, right? So as of now, we consider these two circuits and we apply Kirchhoff's rule first to this circuit and then to this circuit. So we will apply Kirchhoff's rule to both of these circuits. So what do we get from Kirchhoff's rule? In this closed loop, we get VBB is equal to IBRB plus VBE. Similarly, in the second loop, what do we get? We get VCC is equal to VCE plus ICRC. Right? Now let us suppose that this VI is an input which is applied across this VBB. Similarly, V0 is the output which is measured along this circuit. So what we can write? We can say that, so from this we can write VCE is equal to VCC minus ICRC. So what is this input voltage? From this we can see that input voltage is nothing but VBB because this input voltage is applied across this VBB. Similarly, the output voltage which we will measure, that is nothing but VCE, that is collector emitter voltage. What is collector emitter voltage? It is nothing but the voltage difference between the collector and the emitter. Right? So we can replace VBB and VCE with VI and V0 in the above two equations. So what do we get? So this was my equation 1 and this was my equation 2. So now my equation 1 will become VI is equal to IBRB plus VBE and equation 2 will become V0 is equal to VCC minus ICRC. So from this you can see that the input voltage is given by this and the output voltage is given by this. So we can find out a relationship between the output voltage and the input voltage. Well, here the output and input voltage which we are talking about, is nothing but an alternating AC signal which is applied at the input and which is obtained at the output respectively, right? Now let us look at the following scenarios. Now when I talk about VI, as long as my input voltage VI is less than 0.6 volts. Right now I am talking about silicon, right? Now for silicon, what is the cut-in voltage? You remember what is cut-in voltage? Cut-in voltage for silicon is 0.6 volts, right? That means below this voltage, there is no current at all. Even though the voltage increases, there is no current at all. So only after this cut-in voltage or threshold voltage, whatever you call it, the silicon will be, the transistor will be in active state. So as long as this cut-in voltage is less than 0.6 volts, the current is 0. So collector current is also 0, emitter current is also 0, right? So if collector current, emitter current, everything is 0, what happens to the output? So the output becomes equal to VCC, right? So output becomes VCC as long as the input voltage is less than the cut-in voltage of the semiconductor. Now let us look at the second scenario where the cut-in voltage, or when the input voltage is greater than the cut-in voltage of the semiconductor. So what is this state? This is the cutoff state. You remember I spoke about cutoff state of mode of a transistor. When was the cutoff mode? When both the junctions, when the emitter base junction was reverse biased as well as the base collector junction was reverse biased. Okay, we will relate all those things later. So for now, you just understand it this way. Now, when the input voltage is greater than the cut-in voltage, in that case, what happens? In that case, the transistor is in the active mode. And in active mode, what will happen? Collector current will increase with increase in base current. Right? When your input voltage is greater than 0.6 volts, now as your input voltage increases, this IB will also increase as per this equation. Now as IB increases, IC will also increase, right? That is, the collector current will also increase. Now as collector current increases, from this equation, from equation 2, you can see that if your IC increases, that means a greater value is getting subtracted from VCC. Therefore, your V0 will decrease. So that means V0 will decrease linearly with increase in VI. That means as the input voltage increases, the output voltage will decrease, right? In the active mode. Now let us talk about the third scenario. In the third scenario, we see that what happens beyond a very high value. Say what happens beyond a voltage of greater than 1 volt. In that case, the transistor goes to a saturation state. And what happens in the saturation state? V0 decreases non-linearly, because in the active state the decrease of V0 was linearly with Vi, but beyond this 1 volt the V0 decreases non-linearly with Vi. So now if we plot these three variations in a graph, how will the graph look like? Let us suppose this is Vi and this is Vo. So initially what happened? Initially V0 was equal to VCC. Let us suppose this is some value VCC. So it remained at VCC, constant. After that it entered the active mode where it decreased linearly. And then it increased another mode where it decreased non-linearly. So that means you can divide it into the three regions. This is region 1, this is region 2, and this is region 3. So the region 1 talks about the cut-off region. Region 2 talks about the active region, and region 3 talks about the saturation region. right? So we see the variation of voltages in the three different regions of the transistor. Now if I say that I want this transistor to act as a switch, what is a switch? It is basically, if you switch it on, it will instantly change your, that means when you switch it on, that means you are changing the input voltage. As soon as you change the input voltage, there should be an instant change in the output voltage. Similarly, when you switch it off, there should be an instant change in the output voltage, right? So that means if you look at this graph, the transistor can behave as a switch only in the cutoff zone and the saturation zone. Only in these two zones, the transistor can behave as a switch. Why is it so? That's because in the cutoff zone, if you see what's happening, if Vi decreases, so what do we see from this curve? So we could plot this curve based on our explanation. We saw that in the three different regions, what is the value of the V output, right? So what do we see from this? We see that when the value of V input is very small, the value of V output is very high. If you look at it, these are the regions where V input is very small and here V output is very high. Again, when the value of V input is very high, then what happens? The V output becomes very less. So this is the cutoff region and this is the saturation region. So what do we see? That in the cutoff region or in the saturation region, a low input or a high input can switch on or switch off the transistor. For example, when a very low input is applied in the cutoff region, very low input in the cutoff region, the output is very high, and in this region, is the transistor conducting? The transistor is non-conducting because current is zero. So we say that the transistor is in switched off mode. Now look at the saturation region. When the input voltage is very high, the output voltage is very less, right? Now in this case, the current is high, because in this case the current IC was 0. In the cutoff region there was no current, but in this case the current is high. It is the saturation current, in fact. That means the maximum value of current. So now the transistor is conducting and it is called to be switched on. So we see that the transistor behaves as switched off in the cutoff mode and switched on in the saturation mode. So a transistor can behave like a switch only in the cutoff region or saturation region and not in the active region. So only in this region or this region, the transistor can behave as a switch. So what do we conclude? A low input switches the transistor off and a high input switches it on. That is what we concluded from this, right? So I hope it is clear to you that how transistor works as a switch. So first what we did? First we applied Kirchhoff's law and we wrote the equations for both the input circuit and the output circuit. With the help of that, we plotted a graph between the output voltage and the input voltage. And using this graph, we can see that a low input switches the transistor off in the cutoff region, and the high input switches the transistor on in the saturation region. Right? So this is what we discussed for the first application of transistor as a switch. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.